some things you can eliminate. Like this OH, is that a hydroxide? Are you familiar with skeleton structures like this that just show the carbon bonds?
No, just
Okay, this is a shorthand. Like for example, benzene I wrote kind of like this because what is done is like in organic chemistry, you have to fill out the rest of the valence here. So if there's a carbon here, that means I have two carbon-carbon single bonds, and then there are two bonds that are missing. The bonds that are missing are hydrogens. So if I have two single bonds here, that means I have two hydrogens on this. And so that would be a CH2 group, what we call a methylene group. So this is an alcohol here. I have a carbon here and an oxygen. So it's carbon-oxygen single bond, then I have a carbon-carbon single bond, and then I have two more hydrogens attached to this. So this is an alcohol. Alcohol is not a hydroxide. Unless it's like phenol. You know, with phenol, if it's bonded to a ring like this, do you see this is what we call aromatic. It's alternating single, double, single, double. And in this, it's flat, planar with all the p orbitals lined up. And so what we have here is a delocalized pi bonding network here. If it's attached, if the alcohol is attached here, then the electron withdrawing effect of this could make it more acidic. However, this is electron rich. And so this is just an alcohol, so hydroxide's out. It's not a hydroxide. Hydroxide needs an ionic bond. Do you see an acid? Do you see any acidic hydrogens? No, we need an acidic hydrogen. How do you get an acidic hydrogen? You have to have a polar bond. This is polar here, but it's an alcohol. It's not polar enough to be an acid. This is a hydrogen carbon. They show two hydrogens over here. This hydrogen is bonded to nitrogen. This could potentially be acidic, but if you think of ammonia, a hydrogen-nitrogen bond is not very acidic. You know, think ammonia. Over here, this is a hydrogen carbon, as are all the other ones. Those are all non-acidic. And so it's not an acid. So you could have done this by process elimination, one. Or two, you should know about the amines. Do you see the ending on the name here, I-N-E? There are a whole bunch of amines. I don't know if you had a chance to take a look at this table. Oops, I'm logged out. The table, Appendix D is more comprehensive, so let's just go to Appendix D, and it was A30 maybe? Let's see, A30. Let's try that. No. Maybe 829. No. They should have a little table of contents for the appendices. Let's see if I go this way. Do you see all these weak bases? Do you see something they all have in common? Yeah, and then also look at their name and tell me what their name all has in common. Yeah, that's called an ene. I know it's, or and what these are called amines. Amines are ammonia-like bases. All these weak bases are all variations of amine, and they all are ammonia-like. So I gave two examples, I think. I don't remember. When? Let's see. I'd like to give these two examples for amine versus not an amine. And 10, 24, 23. Amines are spelled with one M. And if you have two M's, then that refers to an amine that is what?
It's in a complex, right?
Yeah, it's in a complex. With two M's, this refers to NH3 ligand. With one M, it refers to something entirely different. Organic chemistry is divided into classes of compounds. In organic chemistry, we have a whole bunch of different types of compounds based on the structure. And these structures and composition will lead to specific properties. So we have the hydrocarbons, which are grouped into the alkanes, alkenes, alkynes. And then we have more. You know, we have the aryl, which would be like, these types of groups have these conjugated, network of delocalized pi bonding electrons. That's what you see back over there, etc. These are the aromatics. Aromatics are known. A lot of them have a distinctive odor, etc. And then the common ones are the hydrocarbons that we cover here, just the alkanes, alkenes, alkynes, not the aromatic ones. These are called aliphatic, usually. Aliphatic versus aromatic hydrocarbons. So we just looked at a little bit of the hydrocarbons. This is in chapter 3. And then the alcohols. The alcohols, like methanol, but in general what we say is an alcohol is ROH, where R is the rest of the chain or molecule or whatever, and it's carbon or hydrogen. If it's hydrogen, then it's water, and so I guess we can't say hydrogen in this case, but in other cases we can. This is different than this. This is the carboxylic acid. Group here. And so alcohol is not the same as a carboxylic acid, and the key difference is this. This is called a carbonyl group here. And so we have acids. And then we have bases, and the common bases are the amines. And the amines are going to be R. It doesn't have to be the same R group. R in this case can be hydrogen. And so usually what we do here is we say R prime, R double prime, R triple prime to indicate that they don't have to be the same. And this is R is going to equal carbon or hydrogen. That would constitute an amine, because when we look at the electronegativity, what is the electronegativity of carbon? 2.5. What is the electronegativity of hydrogen? This is 2.1. So they're similar in terms of electronegativity. So having a carbon or hydrogen does not change the delta minus much on nitrogen. If carbon was significantly more electronegative, then it would decrease the delta minus, making this less basic. But if it's carbon, we're okay. And so the example that I use is like this. We can have the amine, or how about if I had chlorines on here instead? If I put chlorines on the nitrogen, does this constitute an amine? No. This is not an amine. Not an amine. And it's because we need this negative charge. Bases, we got this negative charge thing going on here. We need this. This one is going to have positive charge, not negative charge. This is actually delta plus. The charge is flipped. It's not an amine. So when we look at this list of compounds here, all of these are amines. You can tell by the name. The name, and a lot of these are biologically active. So this is hydroxychloroquine. Hydroxychloroquine, there's some recent studies of this, and it actually turned out that this was effective in the treatment of COVID. In retrospective, looking at the data in combination with other stuff. But this is already a drug, and this is used to treat other diseases. And what happens is this gets into the cell. This can pass through the membrane there and changes the pH of the intracellular fluid. And when you change the pH of the intracellular fluid, it screws up the folding of proteins and this kind of stuff and that kind of stuff. And so you don't really want to change it, but I guess if the cell's diseased, then you want to change it. But does this increase the pH or decrease the pH? Intracellular fluid. Increase. Because do you see 1, 2, 3 amines? This is tribasic base. We go back. And so what you do is you don't have to memorize the table, but normally when I have a table, I mean these are just tips that I've seen from experience that because I look like in a class, like I told you I was struggling in a particular class, and I started talking to the person who got the high score and see what they did. And so these are tips that are generated from these like high scorers. I asked them, what they do. And so certain things that you can do to make you like well ahead of everybody else in the game, like me. I mean, they were well ahead of me because I never did this kind of stuff. But the type of stuff you would do is you might look, just at the table. You don't want to memorize any tables, but you want to see, is there some kind of general pattern in the table, that you can see. That way you might be given some weird compound, you might not know anything about it. Like, look at morphine. Morphine's weird, but would you know that's amine? Maybe not. Maybe you wouldn't have known this is a base, unless you might have seen it before. And so what I think, if you're just learning chemistry, the best thing is to see a lot of stuff. If you've never seen any of these, well, if you've seen it once, you might not remember it, but in the future you might, remember some pattern, and the pattern is all the names. And then E, that's kind of common in organic chemistry, ic acid, trichloroacetic acid. Up here, actually, trichloroacetic acid, is actually it's 3 times 10 to the minus 1, 0.3. 0.3, the percent ionization of that's quite high. Maybe it's not like HCl. I said it's comparable to HCl, but that's probably off a bit. But this is trichloroacetic acid. They don't classify it in strong acid, but this is the strongest acid out of all the weak acids here. It's right on the edge. Whereas up there, the strongest of all the weak acids is, sulfurous acid, or above sulfurous acid is oxalic acid. So oxalic acid is borderline strong. And so there's certain things that I wouldn't necessarily memorize, but on there, and the other thing I'd look at is, okay, that's borderline strong, what's his Ka? That's the strongest of the weak acids. Ka is 10 to the minus 2, right? Whereas this one's 10 to the minus 1. So trichloroacetic acid's already got oxalic acid beat. But going on here, so these are amines, so I would just, and there are too many of them. Methylamine is usually one I talk about, dimethylamine. In Chem 1A, there's a homework problem, methylamine versus trimethylamine. Which one would you predict to be more basic? Methylamine or trimethyl? You might predict trimethylamine because it's got 3 electron-rich methyl groups bonded to it. But when you look at the actual data, this is 6.3 times 10 minus 5, whereas methylamine is 4.2 times 10 minus 4. And so I talked about other effects that could occur. In hydrolysis, if you have these big bulky methyl groups on there, it could inhibit collisions. But then if I use that argument, look at triethylamine. And so the book cherry picks some, on some of the questions, it was like, I think it was triethylamine versus ammonia or methylamine or something like that. And you expect these, the longer the chain here, the more electron rich it is. And so you expect it to be more basic. So they picked the one that worked out quite nicely, but sometimes the data doesn't quite agree with that. So it said it was continued, but it wasn't continued. All right, so you could have either done this by a process of elimination or by knowing the amine, either by its name or by its structure.
Are amines always weak bases?
Mm-hmm. But you have things that have both an acid and an amine. We call those amino acids. And the amino acids are base and acid. It's like a buffer. So amino acids like a mini buffer, except they aren't separate. They're attached. And they have interesting pH behavior. At certain pHs, they'll be in the acid form, or they have the Zwitter ionic form, or both. The amine is protonated and the acid is deprotonated, or some weird stuff, with the pH and the speciation of those amino acids are interesting. That is more like in biochemistry type stuff, and so And so we look at amino acids, the acid form, okay, and this is kind of interesting here, and the basic form, not a problem. This is the neutral form. What did they call it? I thought they called this one the Zwitter ionic form. Here's Zwitter ion. Pi is given by the average of the pKa's that involve the Zwitter ion. That gives the boundaries to its existence. So the Zwitter ion only lives between certain pH ranges, and this is an interesting equation here. This is the we have different ways of solving. So one of the equations we use is the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation is when you have a weak acid and weak base that are conjugates of each other. But what if you have what we call an amphoteric ion? When you have an amphoteric ion can go either way. It could go act as an acid, or it can act as a base. So just the very fact that you have something that's amphoteric means that it's kind of like a buffer. It's that the acid and the base are the same thing. That is, the acid is the amphoteric species, and the base is the amphoteric species. So let me give you an example. Bicarbonate. Bicarbonate, which is in our blood, or it's a major player in regulating our blood pH. Well, anyway, bicarbonate is both. It's an acid, weak acid, and a weak base, but it's the same thing. So that's kind of like a buffer in a way, although its buffering action might not be the greatest. But when you have the weak acid and the weak base in the same, we have to solve it simultaneously. And when you solve it simultaneously and you make certain assumptions, we generate this equation. This is the equation when the weak acid and the weak base are the same species. and you solve it simultaneously, which you don't want to have to solve it simultaneously, so you let somebody else solve it simultaneously and they come up with this equation. And this equation, the restriction here is it has to be fairly concentrated for this equation to work. Otherwise, you're going to have to sit there and solve it simultaneously. Did you guys see my post on simultaneous equilibria? You may be interested. There's always some students that can do this, every year, I think, that can solve simultaneous equilibria. But the math is kind of horrendous for me. But you'll grind through the math. This is for problem number 89 in the homework. If you actually wanted to solve it, the key, it's not in the key. They just start it in the key, and then I think they give you the final answer. So I went through it step by step. This is 1.1 times 10 to the minus 5 molar HCN. You have to solve it simultaneously. So what we do is we set up the ice table. I set this up like this before, I think, when we were talking about simultaneous, but I never solved it. I just stopped there. Well, if you wanted to solve it, this is how you'd solve it. And so I go through all the steps here. This was not too terrible, actually, here. Not too bad, unless, what did I do here? I think I used a simplifying assumption, yeah. I used the simplifying assumption, but you could use a method of successive approximations to get a better answer. That's one way. There's another way that you could solve this. And this is called a mass and charge balance. This is the way that you do it in computers. So if you're writing a program to solve these kinds of things, do it something like this, where you come up with as many equations as you can. So I come up with equation A, equation B, equation C, the concentration of cyanide, equation D, concentration of hydronium, equation E, concentration of cyanide, equation F, and then solve the system of equations here. So I go through solving the system of equations here. And then I come up with a cubic equation. Well, a cubic is okay. I could just do that in my calculator. So I just punch this in my calculator. And come up with this answer. Or you could solve it using successive approximations if you don't have a calculator, this cubic equations. All right. But most people don't want to do that. And so they come up, and you can only use these equations for very specific scenarios. What was that equation here? This equation. And so this equation you memorize, this one, because we don't want to have to derive this. If you derive it, you go through something like I just did with the mass and charge balance. You can derive this equation. And it comes out to a very simple equation because the acid and the base are the same species. In fact, we're going to look at this equation today. This is the equation for the pH of an amphoteric salt. And so what they're treating is this is an amphoteric salt. And therefore, how do you do the pH? You got to do the pKa for the, this is called an ammonium analog. So this is like ammonium. And this is like an acetate analog, you know. And so you have an acid and a base. And so, but this is kind of weird though, because usually the acid and the base are the exact same species. In this case, they're actually different species here, but I guess this equation works. We'll see it for the other one. This is for glycine. Glycine is the simplest amino acid. Do you know what the R group in glycine is? Hydrogen. That would be the, so they call it the side chain or the R. And so here we can change the R group. Here's hydrogen. Or no, this isn't some other acid. And so now this is diprotic acid here. It's actually triprotic because you got to consider this one. And so this is triprotic. The same thing with the bases. The bases we look at what can accept things. This is an isoelectronic point. And so you're doing biochemistry, you'd be doing this. All right, other questions?
I have a question on that same one. The hydroxide, what does that mean? What does that option mean? It is a hydroxide.
This one?
Yeah.
Hydroxide means it's the hydroxide ion, so it's OH minus. That's different. Hydroxide and hydroxyl are totally different. Hydroxyl is covalently bonded. Hydroxide is ionically bonded. Let me save this before I lose it. So we have two extremes. This is a covalent bond here. So this is covalently bonded, although this is a polar covalent bond. And then the other extreme would be this. So this unit here behaves totally different than this unit here, even though they're both OHs. And the problem is people see OH and they automatically think this is a hydroxide. No, this is not a hydroxide, this is a hydroxyl. Hydroxyl groups are alcohols, or unless the hydroxyl is attached to a carbonyl, then we call it carboxylic acid. And so this carbon here has to be bonded to, it cannot be bonded to double bonded to an oxygen, because if it's double bonded to an oxygen, it changes the hydroxyl character, because now if we put a double bonded oxygen, which we call carbonyl group here, then this changes it to an acid. This is a carboxyl group. The il is used for substituents. That's the pattern: phenyl, methyl, ethyl, propyl, methyl alcohol, ethyl alcohol. Those are used for substituents. So this is carboxyl here that's attached to the R. But so we can attach this to some bigger structure, make an amino acid or make some other acid or whatever. Hydroxide, that's an anion. And so if I said it is a hydroxide, no, it isn't. Everything's covalently bonded in it. There's no hydroxide ion in that structure. And so that's what I meant by that.
So if you said it was a hydroxyl, would that be correct?
That would be correct. There's a hydroxyl in there, and it would be an alcohol. It could be carboxylic acid. This could be a carboxylic acid if there was a double bond coming off here to an O. Then it's carboxylic acid. Then I would have circled B. But this is not an acid. So I said, is it a base, hydroxide, strong base? Is it an acid? Not all hydroxides are strong bases. Just the soluble hydroxides are strong bases. But anyway. Uh-huh.
Just in terms of scheduling for tomorrow, we're just leaving the test or everything else?
Well, that's it. Okay, what we do for scheduling is going to change what I do for today. The scheduling I could have, I was thinking, because I got behind in lab, I was thinking to move the exam to Thursday, but I don't know if that works for you guys. Does that work? If I move it to Thursday? Because if we do the lab, it's not going to be all tests. We would do the lab the first half of the class, but I need to talk about the reactions first. And so if we do the test tomorrow, then I'm going to talk about the lab today. If we do the test Thursday, then I'll just talk about the lab at the beginning of lab tomorrow. But I don't mind. We could do either. Which was your preference? Test tomorrow in lab or test Thursday in class? Thursday? Mitchell, do you have a preference?
No.
All right, we'll do it Thursday then. And then tomorrow we're just going to do the lab. At the beginning I'm going to spend maybe an hour or less talking about the reactions in the flow chart.
Is that main office hour is tomorrow night instead of today?
No, well, do you want it when? Do you want the office hour right before the test? Tomorrow night?
Right.
Yeah, all right, we'll do the office hour tomorrow as scheduled, 8 to 9. Or what did I have it, 9 to 10? Yeah, 9 to 10 tomorrow. Okay, sure. All right, then I'm just going to talk about this stuff. If you have more questions on the test, I'll talk about that. Otherwise, we'll look at buffers and titrations some more.
Are we still in chapter 17?
Yes. We're still in chapter 17. Are there any other questions on this stuff here? No? All right. Oh, the other thing you should do is read the captions to these things. You'd be surprised how many people don't read the titles and the captions to the tables and figures. Well, let's talk about organic functional groups briefly here. Do you know the ain, the meaning of ain?
Carbon and single bonds.
Oh yeah, all single bonds. Ene,
Double bonds.
double bonds, right? And so with anes and enes here. Cyclo just means a ring, cyclohexane. Naphthalene. Naphtha, this is an aromatic compound here, naphthalene. This has a more complex structure. Then we have aldehydes. Aldehydes, this is a carbonyl group just stuck on there, formaldehyde. So this is just a carbon double bonded to an oxygen, 2 hydrogens attached. This is a very common one for Lewis structures. This is a favorite. Acetaldehyde or ethanal, these are aldehydes. Usually they end in AL. Yes, but this is acetaldehyde. It's like acetic acid in a way, but it's missing the hydroxyl group. Okay. This is gaseous, that's liquid. And then we have methanol, ethanol, phenol, acetone. Acetic acid, benzoic acid, methylamine, aniline. Aniline's a benzene ring with an amine, so this would be a base. Since benzene rings are electron withdrawing, this would be expect to be kind of weaker base than if you had an electron pusher group, on there. Aniline. That's what you would expect. And then you have to look at the data because there are multiple factors affecting acidity and basicity. And we're just trying to do it simply without having to do quantum mechanics or any of that type of stuff, just based on this whole thing with the Lewis structures and valence bond theory, this type of stuff. We aren't doing a full MO treatment of these molecules, molecular orbital treatment. But anyway, like some of these, it's good just to read through them. Then you see the common species that you might encounter in the future. Sometimes the tables are very long. The acids, you read through those as well. Some of these are weird acids, like thiophenol. Thiophenol is like an alcohol, except instead of oxygen, you have sulfur. And I talked about phenol yesterday. Phenol is an unusually strong, an unusually strong acid for an alcohol. Phenol is an alcohol, but it's Ka. You might look at that Ka and go, that Ka is nothing. 10 to the minus 10. That's an incredibly weak acid, and that's true. It's an incredibly weak acid, but it's not an acid. It's an alcohol, and so that means it's unusually strong. As an alcohol. And then you look at thiophenol. This is 10 to the minus 7. Wow, that's a lot more basic. I mean not basic, acidic. That's like 1,000 times more acidic. It's got to be the weak bond here. It's not the polarity. Well, there's also the polarity issue with the phenol. So certain things you might see this pattern. Okay, phenol, thiophenol, and then you might look, which one's stronger. This kind of stuff. This is all stuff you can do if you have the luxury of time. Most people don't have any time to do this. But if you do this, and how long does it take? You have certain little notes that you write to yourself in this table. You write to yourself little notes and then review them every day. Then you remember them. So I would annotate things. Found that pretty helpful. So let's go back to chapter 17. And it's chapter 17 starts off with the common ion buffer, and then we go to, I skipped these right now. I mean, the in-depth calculations for those. And we're just looking at neutralization, titration curves. We're looking at being in the buffer region. So when we have a strong acid and a strong base, these are the types of questions you get asked, usually on multiple choice. If you have a strong acid, strong base, the rise here is big, around from 2 to about 12. From 2 to about 12, that's like 10 pH units. And so 10 pH units of 10 powers of 10 is like 10 billion. So there's a change. You become 10 billion times less acidic, or 10 billion times more basic. Here. The equivalence point is pH 7. We don't call this the buffer region because this is the acid, excess acid with its conjugate base, but the conjugate base is like sodium chloride. Chloride is not a base. It's not an effective base. And so there's not much that we say in terms of the regions here. It's just excess acid region, excess base region. And here we have the stoichiometric equivalence point, and then over here we have the initial acid. When we get to a weak acid, strong base, this is just inverted. You start off with the base in the flask and the acid in the burette, and you use acid as a titrant. And so this is inverted, just flip it. So most of the time is devoted to this type of titration here, which is weak. You can see the rise isn't as good. We end up about the same, 12, right? Because it's just excess strong base, sodium hydroxide, which is high pH. if we're using 0.1 molar sodium hydroxide, the pOH would be 1, and therefore the pH would be 13. So this pH is going to approach 13 at the volume equals infinity, because it's being diluted. It's never going to quite hit there because of this solution dilution. But we start off at a higher pH, so that's why the rise isn't as steep. This is going to limit the number of indicators we can use for this. The number of indicators that we can use for the strong is much more, but here we have to find something. Phenolphthalein is perfect because we form a basic salt. But anyway, we have the initial weak acid. Then this is the buffer region here. The Henderson-Hasselbalch works over this range here, but buffers are supposed to resist, dramatic pH changes. And we're adding strong base here, and you can see it's resisting pretty well in this range here. But when we get to the limits here, the pH changes more dramatically. And so that brings up a couple of key points. One point is something called the optimum pH of a buffer. The optimum pH of the buffer is right in the center here. And so the optimum pH of a buffer is just equal to pKa. And right when we're in the center here of the buffer region, that's when we have equal amounts of excess acid and conjugate base. And so we have a 50-50 base to acid ratio right in the center. And that would be the optimum pH. Because we can go backwards by adding acid, or we could go forward by adding base, and the pH stays fairly flat. Do you see that? I mean, it changes a little bit, but it stays fairly flat. And so that's a good buffer. And so the buffer region is going to extend to about a pH of pKa about +1. So if the pH here is about 4.3, 4.4, let's say 4.4, then we can go up to about 5.4. So we'll go up to about here, and then it starts to climb dramatically. Or we'll go down. If we drop down to, if this is 4.4, we'll drop down to about 3.4 here. And then it starts to drop down more dramatically. And so in this region here, we call this the buffer region here. And so the buffer region is going to be pKa -1, about 3.4 here, to pKa +1, and then it's flat enough. And so this buffer, if we had an optimum pH of about 4.4, then the buffer range would be about 3.4 to 5.4. And then that would be its good usable range. If we go beyond that, two things happen. One is the pH changes more dramatically, and two, it becomes heavily biased. So a buffer over here is heavily biased towards acid. So we have lots of acid but very little base. And so it's not very useful. And over here, the buffer would have lots of base, conjugate base, but very little, the salt, very little acid. And so it becomes a lopsided buffer. Optimum buffer would have 50-50 mix of acid, in this case acetic acid, and base, acetate. It's 474, sorry, 474. Misread that. And so to about 574 and to about 374 would be good. And so we're looking at calculations in the buffer region. And calculations in the buffer region are quite rapid. And so I don't remember what ones I did, I think, in our calculation earlier. Did we finish the pHs, the 10/11ths? Did I do the 10/11ths and the 1/11th equivalence points? Mm-hmm. Yeah. Those are easy because the 10/11ths and the 1/11th are just pKa plus or minus 1. So that's the buffer region. And then what we go to is, we can use that shortcut. So from the equivalence point, the x over total equivalence point, we can get the pH. But how can we go from the pH to the X over total equivalence point? So I want to go back and take a look at this. And so I just want to go backwards, basically. This is what I'm going to try to do. So in other words, let's say I want a pH 4 buffer. If I have a pH meter, it's easy. Just stop when you get to pH 4. Then you have a pH 4 buffer. But what if I didn't have a pH meter? What if I just had to add it? So the question is, how many milliliters do I need to add? So I'll stop at pH 4. pH 4 is still in the buffer region. It's not going to be the best buffer because it's going to be kind of lopsided towards what? To acid. You know? But it's still within the 374 to 574 range. So even though it's kind of lopsided, we are going to have way more acid than base. It's still okay because what we can do is we can up the capacity. So if the ratio is lopsided, then just bump the concentrations of everything up, and so that you'll have enough base to work effectively. Or I might want pH 5. You know, pH 5. This would be really good for pH 5 buffer because we're right there, here, kind of in the heart of the buffer range. Or I might want pH 6, but pH 6 is too far out of the buffer range, wouldn't you say? And so I don't want to go beyond pKa plus or minus 1 because it's going to start really causing more significant pH changes. And so in this case, I think this buffer system would be quite good for pH 5 buffer. So if I have a pH of 5.00, how many milliliters of NaOH do I need to add? And so I'm going to try to make a pH 5 buffer. So there are different ways I can make a pH 5 buffer. One way is just to mix acetic acid, HAC, with sodium acetate. The second way is to do a titration. And so we do an HAC plus sodium hydroxide titration. And essentially what that does is it just makes the sodium acetate, and we just need to make the right amount of sodium acetate. This makes, we need excess HAC. The limiting reagent has to be sodium acetate. So what we're going to end up with is we're going to end up with HAC and sodium acetate, as long as the sodium hydroxide is the LR, the limiting reagent. And then we're okay. All right, so this is the way we're going to do it here. And so we're going to figure out the calculation for this next. Let me do that. So we're in the buffer region. pH equals 5.00 is in the buffer region. It's very important because it depends on where pH 5.00 is expected to be. That's going to dictate how we handle this. Since it's in the buffer region, then we're just going to use the Henderson-Hasselbalch equation for this. So the pKa is 4.74 plus the log of the base to acid ratio. I'll just call it B over A, base to acid ratio. They have to be conjugates. And so we're going to subtract that from both sides. So this is going to give us 0.26.
Where did you get the 4.75?
That's the pKa given. And so I'm going to get the base to acid ratio by just doing this. And so the base is AC minus acetate, the acid is HAC, and that's going to equal 10 to the 0.26, the anti-log. And what does the ratio come out to? $181. I'll just carry 2 digits. 181.97 over 1. So I could do this. I could make this 181.97 molar acetate over 100 molar acetic acid. This would be very high capacity. But possible? I don't think it's possible because the concentrations are too high. This is going to probably exceeds solubility. Or, anything in this ratio will work. It doesn't have to be these numbers, but it just shows these numbers because it make life easier. But as long as it maintains this ratio. And so what I could do is I could do 1.8197 molar acetate and let's go 1.00 molar acetic acid. This would work. It would give me the same pH. Right? What happens if I dilute it with water? If I dilute it, let's say I'm going to dilute it to 0.001897 molar acetate over 0.00100 molar acetic acid. It's still the same ratio. So it's still going to give me the same pH. But what's the difference? The difference is this is really dilute. And so it's not going to be a very good buffer. And so what we say is this is what we call increasing buffer capacity. Increasing buffer capacity is better, but it's going to be more expensive because you have more ingredients in there. There's going to be a limit, the solubility is going to limit how much you can increase the capacity by. But if you buy an overly dilute buffer, it's not going to be very effective because we're going to exceed the buffering capacity of this particular buffer. Well, anyway, we need to get this ratio here. So how can we get this ratio? How we can get this ratio is, this is how much I need to form of the product. So this is a little side here. The side is talking about buffering capacity. The actual concentration in there depends. And so this is the product. This is the excess acid. And so what I do is I do this. I take the 181.97 over 1, let's call it 1.00. It's actually exactly 1. And I convert that into this. This is going to be 1.8197 parts out of a total of 2.8197 were converted into product. And that leaves me with 1.00 left over out of a total of 2.8197. And so what I'm doing here is I'm just totaling it. And so this is the total. And so this is the parts of product out of the total initial. And this is the parts of reactant left over out of the total initial. And then what happens here is this turns out to be the equivalence point here. We define this fraction is equal to the equivalence point. So we've neutralized, out of a total of 2.8197 parts, we've neutralized 1.8197 of those, creating the conjugate base, the product. And then I look at how many milliliters it takes. What did I do? How many milliliters was it? Was it 25 milliliters? I can't remember. I think it was 25 milliliters, right? I took 25 milliliters of acid and then added the 25.0 milliliters. Yeah.
So it's a total, oh,
So 25 out of 25 would be the equivalence point here. This is off a little bit, but it's all right. Or 25 milliliters. This is the equivalence point. The half equivalence point came out 12.5. Is that right? 12.5 out of 25 was the half equivalence point. So what we're going to do is we're going to kind of rescale this. And so the full equivalence point, this would be equal to 2.8197 out of 2.8197. That would be our equivalence point here. So now we're at 1.897, 8197 out of 2.8197. So we have to figure out how many milliliters this is going to occur at. And so this is all I'm going to do. I'm just going to take 1.8197 parts out of 2.8197 is equal to x over 25, because 25 is most. So all I'm going to do is I'm going to take this fraction and multiply by the total. And so x is equal to 1.8197 over 2.8197 times 25. What fraction of the 25.00 milliliters, which would be the equivalence point, are we at? So take this divided by 2.8197 times 25. And that would be 16.133 milliliters. Okay, so this is going to come out 16.13 milliliters out of the 25 milliliters. And so 16.13 out of 25 is the same as 1.8197 out of 2.8197. And so when we hit 16.13, we'll be at pH 5. Does that make sense? Okay. The 16.13 out of 25 equivalence points is the same thing as a 1.8197 out of 2.8197 equivalence point. And we got it. Okay, that only works in the buffer region. Now the Henderson-Hasselbalch we can use almost to the very end. The optimum buffer range, the optimum buffer range is pKa -1 to pKa +1. But the simplifying assumption is valid over a wider range. So this is the range, this is optimum, or the buffer range. This is the buffer range. So we're still in the buffer range. But if we want to use the HH equation, we can use the HH equation almost to the very extreme here. And so the HH equation works over a wider range. And so even if I'm outside the buffer range, I'd still use the HH equation as long as I'm within the bounds here. It's only when we get extremely close, that you don't want to use it. And so like right here and right here, we should use ice. And not the HH equation. That's because the one component is so small, the simplifying assumption is going to fail for that particular component. All right, let's calculate the pH at the equivalence point next. So at plus 25.00 milliliters of NaOH. Forgot if I did 4 sig figs, probably 3 sig figs, I think. And so this is going to be the equal equivalence point. And so the first step is, solution dilution. So we have our 25 milliliters of acid. And we're going to add to this 25 milliliters of sodium hydroxide to 3 sig figs. And so 3 sig figs, we're going to end up with 50.0 milliliters of mixture. And so what does a reaction mixture consist of before any reaction is taking place? So HAC is going to undergo a 25 to 50 dilution of 0.100 molar. So that's going to give us 0.0500 molar. And then the NaOH has the same dilution factor. It's going to be a 25 to 50. So this is going to be 0.0500 molar. And so this is my step I. And then I'll go on to step 1. Step 1, the most obvious reaction is going to be the acetic acid plus sodium hydroxide. It's going to yield sodium acetate plus water. So equivalence point means we have equal amounts. This is stoichiometric, so it's strong. You know, K for this is very, very large. So we're going to lose all this. We're going to lose all this, and then we're going to gain 0.0500. And then what we have left over is just sodium acetate in water. Well, sodium ions are nothing, but acetates are something. So I'm going to skip the ionization here. So my step 2 is just going to be the acetate. And so acetate's all we have left over, and that's a base. And the strongest acid is going to be water. So it's going to be acetate plus water. This is going to yield HAC plus hydroxide. Now take a look at the Kb for this. The Kb is not in the table, so we have to do Kw divided by Ka. What acid should we do the Ka for? Acetic. Acetic is such a common one that I have it memorized, but you don't have to. But it's 1.8 times 10 to the minus 5. And this is going to give us 5.55 times 10 to the minus 10 with Kb. So that's pretty weak. So at equilibrium, I'm going to have 0.0500 minus x. And we'll have x molar and x molar. And so this is going to be equal to the HAC to the first times the hydroxide to the first divided by the acetate first. So this is just x squared over 0.0500 minus x. And then I'm going to use the SA. It should work here because the K is so small. It's x squared over 0.0500. And then solve for x. .26 times 10 to the minus 6. That's going to be the hydroxide concentration here. 5.26 times 10 to the minus 6 molar. 267. I'm allowed, how many sig figs? 2. I'm only allowed 2 sig figs, so that's all right. Should I worry about Kw, water contributing? Should I worry about Kw? Because this is kind of low concentration. So do you think water will be a significant contributor?
Could be. Water's like super small.
What's the max water can be? The max water can be is 10 to the minus 7 from hydrolysis. And it's going to be a lot lower because of the common ion effect. And so we're looking at, like, it's going to be a contributor of like 10 to the minus 8, maybe 10 to the minus 9. And so it's not significant. It's only if this concentration gets lower. Like if this concentration were 10 to the minus 8, then yes, water is going to be a contributor. But if it's a minus 6, minus 7, that's about the limit. We'll ignore Kw. And so we're going to ignore Kw. I'm just going to take the log of my answer. And I get a POH of 5.278. And then that gives us a pH of 14 minus that, which would be 8.721. And drop the 1, and that means that at the equivalence point here, the pH is 8.72. 8.72 equivalence point means that means that phenolphthalein is an excellent indicator. If you look, it's right below, right about 9. And the equivalence point is about 8.72, which is pretty optimum for this particular indicator. And so here, we call this the end point. The end point of the titration is when the indicator changes color or something else happens that's visible. We can't see the equivalence point. We can only see the end point. And here the end point and the equivalence point are just about the same. Pretty close to it. Okay, then we're going to go in the excess base region. So let's pick a volume. That's 25. Let's go to maybe, where do you want to go? Let's go to 25. Should we go 1 drop past 25? 2 drops past 25? Half a milliliter? Where do you want to go to?
How significant is each drop?
Well, let's try it. Let's go 1 drop. Let's say I overshot the titration by 1 drop. What would the pH be? Now it stays red here. You know, it stays red all the way. So you can't tell if you added 10 milliliters extra or 1 drop extra. And so we're going to go 1 drop past. We're going to make an assumption that 1 drop is about 0.05 milliliters. That's something that people calculate in Chem 4. And so we're going to go to plus 25.05 milliliters. This is 1 drop past the equivalence point. So let's just try it and see what happens. And so this is going to give us a total of 50.05 milliliters here. And then let's figure out our reaction mixture. And so we're going to have acetic acid, which is going to undergo a 25.00 to 50.00. I'll have to bump it up to 4 sig figs here. Times 0.100. 50.05 total. So what does that come out to? 25 divided by 50.05 times 0.1. I'm going to carry extra digits, 0.04995. Oh, 499.50. Okay, let's go to the sodium hydroxide. Sodium hydroxide is going to be a 25.05 to 50.05 dilution. 100. Oh, 500,499. Then it just repeats. So we'll go with how many decimal places? 6. Let's just go 6 decimal places out, maybe, or something. And so this will be our step 1 here. This is the excess strong base region. Okay, the limiting reagent is going to be the acid. So we're going to lose all that. This repeats, so I need to change that to a 5, I think. Okay, what we have here at the end of this is we have a strong base and a weak base mixture. When we have a base mixture, we look for all hydroxide contributors. So we're going to have Kb for the strong, which is very large, Kb for the weak, and Kw. And so what we need to do is we need to figure out, is this significant? Are these two significant? Normally we'd say they're not significant because, you know, strong base is going to be completion. And the common ion effect and everything else means that these aren't. But take a look at the difference in concentrations. When I look at the difference in concentrations, I have a lot of weak base, but I barely have any strong base. And so what should I do in this particular scenario? Should I ignore the weak base and just look at the strong? Probably not. And so what we're going to do is we're going to do both. Now sodium hydroxide is just going to is a soluble salt, so it's going to produce the same amount of hydroxide. So the sodium hydroxide is going to produce, and so I'm going to skip the step here. Well, maybe I'll just do it. Sodium ions and hydroxide ions. And so if I start off with this molarity here, and I have 0 and 0, I'm going to end up with this molarity of hydroxide here. So I'll just end up with the, and then I'll put it into the weak base, Kb. You could just do this in your head. You don't have to show me this. I would have just went straight to the Kb, saved myself a step. And so we have the acetate plus water can produce HAC plus hydroxide. And so what I'll do is I'll start off with that amount of hydroxide as common ion. So this is coming from the strong base. 7, 3, 4, 5, 6, 7 zeros and 500, 4, 99, 5. The acetate is 0.0499505. So this is minus x plus x plus x. So we're going to 0.0499505 minus x molar and point this plus x. Don't want to write it all again. So the Kb for this is going to equal x times 0.0 dot 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 plus x over 0.049 dot 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 minus x. I can try the simplifying assumption. Now, there are different things I can try. Which one would you think would work better with the simplifying assumption? This or this? First one. And so we could just do the simplifying assumption in the denominator and leave the numerator. That would save some of the math. Or we could try it for both. I'm going to try it for both. And just calculate what my x is going to be. So I'm going to take my 5.004995 times 10 minus 8 and then invert that times KB, which is 5.55 times 10 to the minus 10 from the earlier problem, divided by 0.049, 0.0499505. Give me an axis point. Did that work? No. This is too big. That didn't work. So I could try the simplifying assumption just in the denominator. Let's see if that works. But I'm out of time, so I'll skip it. It's easier if I had a large excess of hydroxide. If I have a large excess of sodium hydroxide, then I don't have to worry about the weak base. So, you know, if I had, let's say, this is 5 times 10 to the minus 8, but if I had like 10 to the minus 2, you know, maybe even 10 to the minus 3, I wouldn't worry about the weak base. You know, the strong base is going to dictate it. Okay, I'll stop here, and then we'll continue. So tomorrow, I would just read through the lab and then prepare the flow chart in the lab, you know, just with the concentrations. Should be all right. So we're moving the test to Thursday, then, okay, officially.